Hey guys, what's going on? So today we are going to be going over the Ricci Tensor. Make sure to hit that like and subscribe button. Make sure to go onto my Patreon page if you want to see notes and summary sheets coming up on there on a regular basis. Without further ado, let's get straight into the video. So we talked about the Riemann curvature tensor last time. Got a lot of really good comments on that video. There's a few corrections that I want to just bring to light before we dive into the Ricci tensor. As I've noted, as someone noted in the last video, I had written something like this to denote the Ricci tensor, the Ricci scalar actually. So we're going to talk about the Ricci tensor today, but when I had mentioned the Ricci scalar last time, which is what we're going to go over in the next video, I had defined it in this way. This is not right, right? So we actually are going to contract with the metric tensor, okay? And we'll see how that Ricci scalar works. Okay, but in today's video, we're going to talk about the Ricci tensor, okay? The Ricci tensor is a contraction of the Riemann tensor. It's a specific type of contraction, though. So we talked about the Riemann tensor being Rij, doesn't really matter what we call the indices. I like to do alpha, beta for the first two, and then mu, nu for the second two. The point here is that the Ricci tensor is going to be R alpha, beta, alpha, mu, where these two guys are the same. And that if those two are the same, they're going to contract over each other. They're going to sum over each other. This is an Einstein sum. And this is going to become R beta nu. This is the Ricci tensor. Now let's actually get a geometric, intuitive understanding of what this means. Okay. So I want to just put in the forefront of our minds really quick this picture here. So this picture is, we have the Riemann tensor. So the Riemann tensor here, and here we have the Ricci. The Riemann tensor told us something about what happens when we traverse some manifold in one direction and then in a separate direction. And if we come to a point in which the two vectors that were traversed are the same or not the same. If they were the same, then the Riemann curvature tensor was 0. If they were not the same, then there's going to be some distance between the two that can be defined as the Riemann curvature tensor. In this video, we're going to talk about how the Ricci tensor is more geometrically inclined to talk about volumes along a manifold and how volumes compare with each other on a manifold. And what's super interesting to think about, this is just perhaps food for thought, is that the contraction of this object gives us this object here. Okay, this object here is a sphere. We can imagine the volume of a sphere shrinking and growing as we traverse some manifold. And that is inherently related to this guy right here, which is represented by the Riemann curvature tensor. So this is a picture I want to keep in mind. And then when we get into the Ricci scalar, the Kretschmann scalar, and all these different types of scalars and different types of tensors, we want to keep in mind how we can sort of geometrically picture these things, okay? Insofar as we can picture them. Sometimes we can't really intuitively understand what some of these scalars are going to mean, but we can get some sense of what they might allude to, okay? So I'll erase this, and this is a picture that we want to keep in mind. We want to keep in mind that this here, this guy right here, and this right here are related in some way. Okay, so let's set up the problem. So to set up the problem, again, you can get these notes on my Patreon page. There's going to be extra notes coming out on the Patreon page as well, where things are summarized in different ways so that you can remember things a lot easier. The idea here is that, okay, so we're summing over j and k for these first two vectors, right? So the first two vectors if we take a look here, u and v, those are those two input vectors that we're putting into this Riemann curvature tensor. Okay, those represent sort of the two directions, and then this v here is going to be the vector that we're actually transporting, right? So that vector doesn't really live on the manifold. So this is a little bit of a misrepresentation, but this v is in a tangent space on the manifold. Okay. So this v is in a tangent space on all these v's are in tangent spaces on the manifold. So all of them are in tangent space on the manifold. It's just that these two represent the directions, and then this one represents the one that we're actually holding as we traverse the manifold. Okay, and this is that index, and these two are the other two indices. And what we get out of this is a vector. Okay, what we get out of this is a vector, right? Because this is a contravariant vector. Okay, and that contravariant vector again is this guy right here. Right. Anyways, so we're going to start, so we're setting up the problem. We're going to say that the curvature, I'll erase these. We're going to say that the curvature is related to the velocity, right? So if you remember, the velocity is in the tangent space, so we are the velocity of some curve, parameterized curve. If you were to say the location of the curve depends on where you are in the curve, right? So that's the parameterization. Well, the velocity lives in the tangent space because it's the derivative. Derivatives are tangent to the actual curve. So we can be justified in making this claim. And when we do that, and these two guys here, this epsilon, are these, if I go up here, are these epsilons up here. So we're traveling some small distance on a manifold. That small distance is encoded in this epsilon. We get epsilon squared because we're multiplying both of these, right? So this epsilon squared, that's this guy right here. So we can define the acceleration as a change in that velocity. Okay, the change in the velocity. We can divide both sides by epsilon, and so we dividing both sides by epsilon. And so this is how we define the acceleration, right? The change in the velocity over some distance that's going to go to 0, right? And so this here, right? This here again is this right here. Okay. So imagine now dividing both sides again by epsilon. So we divide by epsilon, divide by epsilon. We have to divide both sides by epsilon. That's how we get this right here. Okay, so this is all, again, just algebraic manipulations. And we get to this point right here. And now we're going to do a little bit, not really sleight of hand here, but I'm going to now depart from this blue square, and we want to define a few things. So we're going to picture this. What we're going to do is we're going to propose that here, this is the volume. We're going to say we know somehow that this is going to represent some volume. And when we do that, we're going to say the radius, okay, this is the rate. So these are going to be initial conditions for the dynamics of this radius that represents a volume, or that is a parameter of some volume. So this radius is going to be some initial radius plus 1/2 the acceleration times epsilon squared. This is kinematic equation, or a dynamic equation that you learn in physics 1. Okay, the derivative of this with respect to epsilon is going to be the acceleration, right? Because you just take the derivative of this. This is the derivative. This is 0. And then the second derivative is going to be AI. The initial conditions, if we say at epsilon equals 0, is going to be R naught, 0 here, because there's no, this is 0, if we put in 0 here. And then R double dot is going to be the acceleration. So if we take all this into consideration, what we can do now is we can say the limit of r dot over r, so that's r or double dot over r, is going to be this over this, okay? So it's going to be that over that. Well, we can redefine this to be this right here, because these two guys will just cancel and we get this again. So this is a little bit of sleight of hand, but it works. It's an algebraic manipulation that works. And let's keep on going with this, because what we can do now is we can say, well, we know this guy because we defined it up here. That's just a Riemann curvature tensor with all these input vectors, right? So the Riemann curvature with all these input vectors, that is this guy right here, and then we have this out here in front. So the limit of the double derivative of some radius of a sphere over the not double derivative, right? This is just the spatial part is good. So that is equal to this right here, and so this is related to the Riemann curvature tensor. All right. So we've set up the problem, we've talked about the initial conditions. Let's continue. So the volume of an n-sphere, this is going to be a little bit weird. I'm sort of just giving you these equations. This is more of mathematical sort of brute force calculations that you can do on your own time. This is all given on Wikipedia also. I'm just going to give them to you right here. So the volume of a sphere, of an n-sphere, so this is a sphere in any dimensions, is given to this. And you'll be able to see that this, in 3 dimensions, this will reduce down to your typical formula for volume, right? What's that? That's 4/3 pi r cubed. And so in 3 dimensions, it'll reduce down to that. The point here is that this is the volume, this is the derivative of the volume, and this is the double derivative of the volume. And when we divide this guy by this guy, this is going to cancel with this. We have constants that'll cancel, and what we end up with is just the double derivative over r. Okay, the double derivative of r over r. Well, that looks oddly familiar. That's this right here. Well, and so that means that the volume, we're sort of justifying how this is a volume now. We're saying that this is related to this, which is related to the Riemann curvature tensor. Okay? So putting things together, we said this was equal to this, which is equal to the Riemann curvature tensor. And so if we can contract, right? So we can contract, we haven't contracted here, but we can contract here, I over I, right? Because we have I over I, and this ends up being the Riemann, or the Ricci tensor, okay? So we're picking a direction here, essentially. We're picking the direction of, if we just go back really quick, this guy right here, we're making that I, UI. So we're going in the UI direction. We're going in the UI direction, and that's what gives us this Riemann, or this Ricci tensor. Sorry, this is the Ricci tensor, right? Because we're contracting over both of those indices, both of these indices right here. All right, so that is the Ricci tensor. And so the Ricci tensor is related to the change in the volume of some n-sphere over the volume of the n-sphere. So the double derivative of the n-sphere over the end sphere. Now, let's take another look at this. Let's go back to this picture. So I've sort of cleaned up this picture a little bit. I've taken out the sphere, and I want to look at this a little bit differently now, because we're going about this in two ways. So in one way, we sort of did this brute force, setting up the problem, directly looking at how this is related to volumes. Now we're going to do this in a little bit of a different way, right? So, and this way is going to involve geodesic deviation vectors, and we'll get more into geodesic deviation later on. However, these geodesic deviation vectors are going to be given by these blue vectors here, and we're going to call them S. Okay? And so, let's begin. We are going to say, this is all going to come from the fact that the change in some vector along its own direction is going to be 0. Because it's going along its own direction, there is going to be no change. Okay? So we can take the double derivative. We go along its own direction, and then we go along the direction of S, which is that geodesic deviation vector. And we can add 0 to it, right? So this is just adding 0. We can swap these two guys. I don't really think I've talked about this before, but I will talk about this in a video that focuses more on a little bit more on the covariant derivative. We've sort of talked about the covariant derivative at least a little bit. I'm gonna make another video that goes into it a little bit more abstractly, but the idea here is that the derivative of v in the direction s is the same thing as the derivative of s in the direction of v. Okay. In other words, there's sort of this commutation relationship that needs to hold, and when we do this, we're going to get this equation down here. This here was the Riemann tensor, right? This is the Riemann tensor where we input those two vectors. These are the two vectors we're traveling along, and then this is that vector that we're holding as we're traveling in those two directions. That's in the tangent space, right? So this guy, they're all in the tangent space again, right? They're all in the tangent space. Two represent a direction we're traveling in. The other one represents the actual vector that we want to take the derivative of. Okay? So we get this equation, okay? And we take this to one side, and we're seeing that the Riemann curvature tensor is actually the double derivative of some geodesic deviation vector, this guy, right? So on one side of this equation, we have geodesic deviation, and on this side of the equation, we have the Riemann curvature tensor. All right, so let's go a little bit further with this, because the idea here is that geodesic deviation vector, that's this blue vector that we've defined right here, and we can take that blue vector and now take a look at what this means. So geodesic deviation, we're going to define this thing called the sectional curvature, which is K. Okay. And this is a section of a manifold. Here we have our Riemann curvature tensor with a dot product on S, right? So this guy dot product on this guy, okay? So this is going to give us some vector. That's the Riemann curvature tensor is going to give us some vector that we will take a dot product with the deviation vector. Okay, and what we get is so this is the sectional curvature. We're defining it in this way. Now let's take a look at what happens when the sectional curvature is less than 0. When it's less than 0, say we're standing at some point P, the sectional curvature is going to look like this, where we have the geodesic deviation vector is getting smaller and smaller, right? Because this numerator is getting smaller if this is less than 0. If it's greater than 0, well, the geodesic deviations get bigger and bigger, right? Because, again, this numerator is getting bigger. And if it's 0, then there's no change in the geodesic deviation vector. So we have these three conditions where the sectional curvature can be either less than 0, equal to, or greater than 0. And in each case, they tell us what's happening to a certain plane on the manifold, right? So again, this manifold can be multi-dimensional. In this case, it's only two-dimensional, right? But the Ricci tensor, again, we've thought of it, we sort of thought of it as a volume. So we're going to say that this is the sum of all the sectional curvatures, with one of the input vectors being basis vectors. Okay, and that basis vector is what's going to contract with our Riemann curvature tensor. Okay, I'm sort of going over this in a sort of a light-handed way, just to make things a little bit, hopefully a little bit easier to understand. But the idea here, again, is that the sectional curvature, we input S and V. We're replacing S now with a basis vector, and we're identifying that basis vector with the direction, right? The direction here. So one basis vector, right? So this is going to be say E1. This direction is going to be E2, and then we're going to have an E3, E4, E5, as far as many as you can think of or as you want to. And again, in GR, typically only goes to 4 dimensions. But the idea here is, again, we're summing over I. These are the basis vectors, and that is what's going to make the Ricci, that's what's going to contract the Ricci, or the Riemann curvature tensor to the Ricci tensor. Okay, this is that contraction right here. Okay. If you guys are interested in some more details on how that works, then I might consider making another video on that. But again, the point is that the contraction, this is the contraction step, right? This is the contraction step where we identify the geodesic deviation vector with EI, okay? The Ricci tensor tells us, therefore, how a volume element changes in space, because this is a volume element, right? So we've identified these guys as basis vectors, and we're adding them up where, because they're orthogonal to each other, we can picture them in this way. All right, so in the case of the Ricci tensor being less than 0, we have, just like in this case, sort of this convergence that goes to from a small volume to, or from a large volume to a small volume. If it's equal to 0, then the volume is actually staying the same. The way I've depicted this here makes it look like it's getting bigger. However, in this case, in the case of the E2, say this is the E2 direction, these guys, I've tried to make it look like so that we are looking at this situation in one section, and then in this other section I've made it look like we're going in this direction. So the net result is that we have Ricci actually equaling 0, the Ricci tensor actually equaling 0. So the volume stays the same, the shape not necessarily, and that's going to be important, right? Because the shape is going to be encoded in something a little bit different, which is going to be the Weil tensor, and we're going to talk about that as well. And so, and then we have the Ricci scalar being greater than 0. That's where volumes get bigger, right? So this here is the Ricci tensor summation, or the sort of the the point that we're trying to get at with the Ricci tensor. So if you guys like this kind of content, make sure to hit that like and subscribe button. Make sure to go into my Patreon page where you can see all of this on sheets of on notes. You'll be able to find summary sheets as well, where I also provide information in a summary sort of way. Okay. So with that being said, I will see you guys in the next video, and make sure to like and subscribe to my channel as well.